LC circuit, coil and condenser. Coil responsible for 90-degree lagging of current and condensers responsible for 90-degree leading of current, and both are here like this circuit L and C. It is series circuit, and in series, the current is always in the same phase in all. L and C both are in series, so current is going to be same in both. What is going to be different is the voltage. Voltage will be either 90-degree lagging or 90-degree leading. In coil, current lags behind, that means this is VL, and in condenser, current leads ahead. That's why this is going to be the voltage in condenser. Two are going to be opposite, but you are not sure whether VL is greater or VC. It is going to depend on the values of XL and XC. You see, if XL is greater, this will dominate, and the total circuit would be said to be inductive in nature. If XC is greater, remember I is same, so in order to find voltage across L, you will use this relation. That's why I say directly that if XL is greater, VL would be greater. VL is greater means this is going to dominate. You will say this whole circuit is inductive in nature. Likewise, if XC is greater, the whole circuit will be capacitive in nature. In order to find the total value of X, you will take the difference. Difference I am underlining because if XC is greater, you will subtract XL from it. It is likely to be 0 also, depending on one very specific condition in which both become equal to 0, and that's what we call resonance. We'll study later on. Now let's see, L and C, both the circuits are connected in parallel combination as shown over here. In parallel, the voltage is going to be same in all. In both the branches, not only two, if there are 10 branches, then also we are going to conclude that voltage will be in same phase in all the branches. Then the difference is likely to be with the current only. You see, current. Now, in coil, the current lags behind. So, this is going to be IL. In condenser, the current leads ahead. That's why it is going to be IC. Again, in order to find the total current, you'll take the difference of the two depending on which one is greater. But I is going to be here Vrms upon X. Similarly, here this one Vrms upon XL and Vrms upon XC. It's common. The net value of X will be obtained by using this relation. Here the effect is going to be inverse. If XL is smaller, IL would be greater, and you'll say the circuit is inductive. Means XL should be smaller in order to get the circuit of inductive nature. If XC, capacitive reactance, is smaller, then in that case you would say that the whole LC circuit, which is in parallel combination, that becomes capacitive in nature. For capacitive nature, XC should be smaller, remember. Now, since we have studied reactance in detail for L circuit, C circuit and LC, that too in series and parallel, we must know what is X basically. Actually, it is substitute for resistance. Whenever there is L or C or both in the circuit, you are not going to use R in place of resistance, you will be using term reactance. 1 upon X, this will be called susceptance. Then LCR circuit, we are using all the three, but in series combination, again the current is going to be same in all, and the voltage of resistance, current, both in the same phase. Already you know. Only the difference that you'll have to consider is that a voltage in coil and condenser. But in coil, voltage will lead, in condenser, the voltage will lag, and you'll have to take the difference of the two, whichever is greater. Just suppose VL is greater, then in that case, you'll find the net voltage. Let's see, it's over here. Suppose the phase difference is phi, then cos phi would be given by VR upon V, that is R upon Z. This is called power factor. Power factor will depend on value of Z, and that will be given by XL minus XC whole square plus R square. Similarly, in order to find the net voltage, you are going to use the relation V square equal to VL VC whole square plus VR square. Now, one very interesting situation arises when XL and XC both are equal. Then in that case, you see Z becomes minimum, and basically then it's equal to R only. When Z becomes minimum, obviously the current is going to be maximum. This current will be maximum. This is the case of resonance, and in series, whenever there is resonance, the current becomes maximum. That is why this is also known as amplifying circuit. That figure has been shown over here. The current is maximum. With the increasing frequency at a particular point, you find the current suddenly to be maximum. This is known as the peak of the resonance. This side, the current is increasing with the increase in frequency. Already we have covered that this is inductive nature. Here, with the frequency, the current is decreasing. Obviously, it is capacitive nature.